Okay, so this is the idea. You have to connect thermal loads for heating and coolings, uh, the COP and EER, the coefficient of performance or the energy efficiency ratio, and the electric consumption. There will be something in the middle, so there will be electrical power, and then electricity consumption. Let's say that this is energy, and finally we can connect the electricity bill. In dollars. Okay, so we have to connect all these. So from BTU hours, we need to calculate dollars. Everybody understands dollars, but our clients won't understand the BTU hour. What is a BTU hour? We don't know. But what is a dollar? Oh yes, I know what a dollar is. So from the thermal power, then we need to calculate the electrical power. So the electrical power is we have to use if we are using BTU hours as a thermal load, then we need to use the EER. If we are using kilowatts or watts, international units, we can use the COP, because what we have to do is to turn BTU hours into watts. Okay, so here we have to divide this. If this is my thermal power, the electrical power is the thermal power divided by EER in watts. Okay, if we are using BTU hours, then we need the EER. If we are using watts, then we need the COP. Life would be easier if we were all using the COP, but we have this BTU hours. So what is the electrical power? And then we need to, well, what is the typical EER? It can be 10 to 15, okay, 10, something like that. It depends on the heat pump, but a typical EER, well, this is quite low. 15 is better, 20 would be even better, 10 is acceptable. So what is the electrical power? So it's 45.2. So it's 4,500 units watts. Okay, so this is my electrical power. So my the machine, the heat pump, is giving me, I'm heating up my room, and this is the power, the thermal power. Okay, so this is what it's the machine or the heat pump is delivering, 45,000 BTU hours. And what is the electric power? It's 4,500 watts, because this energy efficiency ratio is, well, this is BTU hour per watt. Okay, the units of this ratio is BTU hour per watts. So if it's 10 BTU hours per watt, so we have 4,500 watts. Now, what is the energy? The energy depends. This is our power. This is 4,500 watts times how many hours? Let's say 10 hours per day times 30 days per month. Okay, so what is the energy? It's 4,500 times 10 times 30, it's 1,350,000 units, watt hour. Watt hours, millions. That we don't know what million is, so it's easier to remember 1,350 kilowatt hours. Okay, so this is the unit that we pay for. And now, what is the price? Or this is the monthly electricity bill. It will be 1,350 kilowatt hour times, let's say, 0.2 dollars per kilowatt hour. Okay, so this is 1,350 times 270. $270. Okay, so this is what we have to do. So we have to start calculating the thermal load. This is building science, building physics. So we have a thermal load, we have the U value, we have well, a lot of things. We have the ventilation load. We can do this with so we have done it with in ART 260. You remember that we calculated the U value, the area, indoor minus outdoor temperature. In this course, we have done something different because we are working with these air systems. So we are calculating the CFM, then the indoor and outdoor enthalpy. Okay, so there are different ways to calculate this thermal load for heating or cooling. And eventually we're using this Excel file, okay? So here we have the indoor, the outdoor temperature, indoor, outdoor enthalpy, the number of people, the CFM, and we calculate the ventilation load. So the maximum number here is what we have to use. Then we have to select a heat pump. Well, first we have to select the systems. This is what we are doing in this course. We are selecting the system. If we are working with a heating system, it can be either a boiler, we can burn something, or we can use electricity with a heat pump. What is the best? Well, there are good points and bad points in every decision that we can make. If we use electricity, we don't need to burn anything on site. We can use PV panels, and we can have zero energy buildings without any CO2 emissions, because all the energy that we need, it's electric energy. We generate this energy in our site. So we have a zero energy building with zero CO2 emissions. Perfect. If we have a boiler, we have to burn something that doesn't emit a lot of CO2 or a lot of greenhouse gases. In this case, the methane or the gas is the best option. It's better than coal, it's better than oil, it's better than biodiesel. Okay, we can use pellets, we can use pellet boilers. We emit CO2, but they are made of wood. Wood is renewable. Okay, so with boilers, we don't need to calculate this. But if we are using heat pumps, we need to turn this thermal load into electrical power. And that depends on these coefficients, either the COP, if we are calculating this in international units, or this EER, if we are calculating this in imperial units. Okay, so we have we have the thermal power divided by the EER, and this is the electrical power. And then the electrical power, we need to turn this into energy. So the energy is power times the hours per month. So 10 hours per day times 30 days. So this is the power. These are the units, watt hours. We have to divide this by 1,000, and we end up having kilowatt hours. And this is what we pay for. We pay for a kilowatt hour. We don't pay for a BTU hour. We don't pay for watts. We pay for kilowatt hours. And then the monthly electricity bill is this times the price of electricity. So think about this. If we had a PV array in our building, and this PV array is producing all these, we are saving, in this exercise, we are saving $270 per month. In this, we are saving $466 per month. Okay, so having a building that runs on electricity and having a PV array that produces all the electricity that we need, it pays off, especially because the price of PV panels, the cost of PV panels is going down, it's dropping because of China, because they are manufacturing thousands of millions of PV panels. Okay, so this is if you need to understand something about this course, it should be this exercise. Okay, so you can calculate heating and cooling loads, you can do that. But if you take building science 2, the solar design, we will do this with Revit. Okay, so even heating and cooling loads, if we have a Revit model, there is an option that Revit can calculate the thermal loads. But if we, in Revit we can select the heat pump, so we can select the COP or the. Okay, so if we are using Revit, even these calculations, we don't need it. But I think it's useful that in this course, at least you can learn where this comes from. Okay, so it comes from the heating loads, then this coefficient of performance, and then we have power, then we need energy, and then we need dollars. Okay, so if you had to know something about this course, is how to turn BTU hours into dollars. So we need to do all this. Okay, now about the Revit file. So there are two things that I want to explain today. On Tuesday, next Tuesday, I would like you to I would like to review what you have done with the final assignment. Remember that you have calculations and you have a Revit file. So if you can submit on Canvas both things on assignments. Yeah, we have this final assignment. So in this final assignment, you have to calculate and then you have to submit the Revit file. You can upload both on this on the same assignment, or if you are working in group, you can, one of the group components can upload the PowerPoint, the other one can upload the Revit file, I don't mind. But I want to go over this first. You remember that we have, if we look at the assignment, this building, okay, so we have to do something like this. We have this pink duct is the supply and the blue one is the return. As you can see here we can have a conflict because we have an intersection between the supply and the return. So this can happen. So we have to figure out how to change the level. So this can be the supply and this can be the return. So the intersection doesn't happen. So, and this is what I want to do now in Revit, because again, it's not difficult, but this is what the coordinator will be doing. Okay, so if we don't pay attention, if we are not good professionals, we need a supervisor to check that what we have done is correct. If we were living in a perfect world, we wouldn't need a supervisor, but we are not perfect. So that's why we need supervisors and supervisors of the supervisor. And eventually there's a boss that supervises everything in theory. Okay, so I want to go over this, and I think it'll take 20 minutes, no more. but I think it's worth explaining that. So you remember, this is what we have done so far. Yeah. So you remember that we need to, from the air handling unit that it's here, we have the supply duct through the shaft, and then we have to go below the slab level. So there should be air between, this is the slab and this is the duct. Okay, so there should be space here. So we cannot go through the slab. That's another mistake. So we are working with the elevation of this. And you see that the middle elevation is negative 17 feet. Okay, that's fine. I think it's better if we work with flex ducts. So let me get rid of this. And okay, it's better. And now we have to connect all these supply ducts to this. But if you remember the assignment, okay, so here we have this data. And now here. And here we have the occupancy. Okay, so we know that the flow, the airflow, depends on the occupancy. So we have from 20 to 30 CFM people, sorry, in this classroom. And here we have from, so in each classroom, we have 20, let's say 20 people times 20 CFM. So the supply airflow that we need is 20 times 20, it's 400. Okay, so this is the first thing we have to do. We have to select the supply diffusers, and here we have to type 400. Okay, that this is another supply diffuser. So this is 400. And this is another one, and it's 400. What about the office space? Do we have 20 people here? No, in this office space, we only have 4 people, 4 and 4. Okay, so 4 times 20 is 80. So for these supply diffusers on the, in the office space, so this is a supply diffuser, and each supply diffuser is 80. The CFM, it's 80. So I select this is 80. And I select this one. And this is 80. Okay, so now we are good with this. And now we have to check the speed. So here the supply diffuser, the CFM, it's 400. And if we click here, the flow is 400, that's correct. And the velocity is 1,145. Is it good? Okay, so that's why we need to connect things, because now we have to connect this to this table. So we're talking about the branch duct, and the speed should be from 200 to 500 or to 600. And the speed here is 1,000. So it's too much because it's a 8-inch duct. So we have to change this. So let's make it 12. If it's 12, now the speed is, the velocity is 500. Okay, it's not bad because it's, yeah, it's below 590. Okay, so at least the diameter of this flex duct at least should be 12. Okay, so now we have to connect. If we go to level 0, we have to connect. Look at this. This is the return because the air is going in, and this is the supply because the air is going out. Okay, so we have to connect this supply diffuser to this duct here. Is it good? It can be better. So let's delete this. And now we have to rotate this T, so you know that there's a, okay. So we can rotate so that we have these two elements facing each other. And now we can draw the flex duct again. And by the way, this has to be 12. Okay. And finally, we have this one, this supply diffuser that has to be connected here. I don't know, in other versions of Revit, I think the view range is not working well. View range, top unlimited, no, double clicking. So if this is the supply, we have to connect this. So let's do it again. Flex duct here, 3D. Select the T, rotate, and now connect this with flex duct here, diameter 12. Okay, so now I think we are good. Well, if you look at this, but this is up to you, you know that there are more supply diffusers here. Okay, so we have this office with 6 people, and according to this, there are like 1, 2, and 3 more supply diffusers. I think 2 would be enough, and here there are 2 return diffusers. Okay, so you have to extend. This elbow is not working now, so we have to extend this. Then we can connect this to this. We have this T, and if you see this, this branch is thinner than this because the airflow that we have for the office, it's very little. This has to be very thick because we have the classrooms. Okay, but here we only have the office, so probably we can shrink this one. This is 20. Let's make it 12, and probably it will work. Okay. Okay, so now we have to connect these supply diffusers to this, and this is for the office space. So there's a supply diffuser here. If we draw a flex duct here, I think it will be the same. Yeah, I don't like this. So let's rotate this one, flex duct. But now this is 8. Is it enough? So let's check the speed. Okay, so the velocity here is 200. It's fine. Okay, so this doesn't have to be 12 because the airflow that we have here is only 80. It's not 400. Okay, so this is fine. So we can have an 8-inch duct here. And now we have to do the same with this one, flex duct, and the same with this one. Flex duct. And now I have to fix this, rotate. And this one, rotate. There you go. Okay, so this is the supply, but now we have to deal with the return, and we have to be careful because we can have these intersections. So how can we do this? We can work from the east elevation. Well, first let's see this. So this is the return duct, and there's a shaft here. Okay, so we need to go down through this shaft. And then we need to go down through this shaft, and immediately we have to go, because this is the corridor. Okay, so they have to run parallel to each other. But if they run parallel to each other, if we go in this direction, we may have a conflict here. So how can we prevent this from happening? Probably we need different levels for the supply and the return diffusers. So the elevation of this is -17. So I'm going to draw another duct in this direction, but now the elevation, I want it to be below the -17. So let's make it -19. Okay, if you type here -19, immediately you have a vertical duct, and then you go in this direction, and then you are now in the corridor, and you can go this way. So now we have to check this intersection. Okay, so I think it's working well. Let me see from the front. Yeah, it's working well because this is the horizontal return duct, and this is the flex duct here. So apparently there is no conflicts. So there are no intersection, and it's working well. But now this is the false ceiling that we need. Okay, so that's why we need to check this, because that is, if we have to place a false ceiling, it has to place here. If we want to have these ducts exposed, okay, that's fine. But if we need to cover this with a false ceiling, we need to understand that this is this duct is lower than this one, because now we have to connect the duct here. So let's do it again. So now we have this this duct. By the way, as you can see, it's within the wall, so we have to move it here. Yep. Okay, so now we have constraints. We have space constraints and stuff. So we can go all the way here. With this one, there is no problem because the only thing we have to check this intersection. So from the 3D, I can connect this supply diffuser to this. But now I have to connect this one to that one. Okay, let's do it. Okay, so I have connected this. I have another return diffuser here, and somehow I have to connect it here. So either we have a T, I think that would be the right option, having a T here, connecting this one to, and that one. Yes, I like this. Okay, so I can place fitting around T. We're done. Okay, I don't know where the hell this T is, so let's make it different. Okay, so I draw duct. I don't want an elbow. So if I have this, and then I connect it here. Okay, so now I have the T, and now I can connect a flex duct here and another flex duct there. Okay, that looks better. And here we don't have any conflicts, but now I want to connect this and that. So how can I do it? We can draw a flex duct first here. And another flex duct here. Okay, this doesn't work. I have to rotate this. Rotate again. Again. Okay, so now this one works, but now I have to connect this one here. If it's too complicated, we always can move this so that I avoid this intersection with three things on the same point. So let's do this, draw flex duct, connect it here. Let's see what happens. Okay, I don't like it. I have to rotate this one. Okay, and now I draw flex duct here. Okay, I think it works. And this has to be 8. And this has to be 8. There you go. Yeah, because this is coming from the office space and this is coming from the classroom. Okay, so that works. This is what I wanted to show you. Yeah. This is the supply duct, and this is the return. But there is no intersection between these two ducts, okay? Because the level of this duct is lower than this one. Here we can see. I think if we shade it, it will be clearer. Okay, so the important thing is that we don't have intersections. So at the end, it's cool. I mean, I like it. So it's a shame hiding these ducts because after all this effort, it looks good. So having exposed ducts, I don't know, it's an option. But the most important thing is that you don't have intersections, and sometimes if we have this perpendicular duct here, we need to make sure that there is no intersection between the supply and the return. Okay. So this is almost done, and then once you are done with this, you can copy all these to the first floor, and that's it. And finally, before moving to the test, there are other aspects that we need to take into account for this. So you see that we have the pink ducts. This is the supply. We have the blue ones. This is the return. And we have this yellow, and this is the exhaust. And the exhaust comes, the exhaust duct that has to go all the way up, because here on the, yeah, so we have the toilet exhaust pipe, and it has to go all the way up to the roof. It comes from the toilets. Well, there is a concept that we need to understand in buildings, is the concept of negative pressure. What is negative pressure? Okay, so the pressure, the air pressure inside this room is lower than the air pressure outside the room. Does it make sense? It does, especially when we are talking about toilets or we are talking about kitchens. Okay, so the pressure inside the toilet has to be lower than the pressure outside the toilet. If this pressure is lower, then the air from the corridor will enter the toilet. If the pressure of the toilet air is higher than the pressure of the corridor, then the air will go out. So usually we don't want the air from the toilet to go out and to spread around, through the building. We don't want that. So we need to create a negative pressure here. So how can we do that? We need an exhaust pipe. Okay, so we have this supply air. Okay, so we supply air in rooms where people are living, the classroom, the office space, even the lobby or the corridor. But in toilets or kitchens, we don't have supply air. We have, but it's not return, because return means that we connect this to the air handling unit, and we don't want that. So we want to get rid of that air, because yeah, we want to get rid of that air. So we need to insert, and this is something that you have to do because it's not in the original file. You have to load a family. You have to go to mechanical, airside components, air terminals, and here you will find the exhaust grill. Okay, so you remember that we have the supply diffuser, we have the return diffuser. So you have to insert the exhaust one. So you open, and now in systems, air terminals, there will be an exhaust grill here. And at least we need, how many? I would place 2 per toilet. Per toilet, no, per restroom. Okay, so you can see that if you insert supply, you have the cross here. If you insert return, we have this bar here, and the exhaust is something like this. So it's different. Okay, so looking at the plan, this is the supply, this is the return, and this is the exhaust. So there are 3 different air terminals. And now what do we have to do? We have to create another pipe or another duct. We can change the elevation. It's 0.4, let's say 2 feet. And then we have to go all the way here, and we just can connect through duct. We change the elevation to, and then we have a T, another one, and another one. There you go. Okay, so from the toilet, we have this exhaust duct. Oh, mierda, I made a mistake. I made a mistake because I didn't change the elevation, so it's on the floor now. those diffusers are on the floor, so I have to change this elevation. Where's the elevation? Here, 29. Okay. So now on level 0, I can draw that. The elevation it's now 9, so let's make it 11. Over here. And now elevation 11. Okay, now it makes sense. Okay, so I have to get rid of this air inside the toilet, but I don't have to connect it to the supply or the return air. So that's another duct. And now looking at the top view. Okay, so there's a shaft here. So from this one, I need to go up, draw duct, diameter, elevation, say 40. Okay, and I get rid of that air. Probably I don't need such a. There you go. Okay, so this is what I wanted to explain today. We need this exhaust ductwork coming from the toilets, and this is for every public building, or even in residential buildings. We don't have an air supply in the toilet or in the restroom. We need to get rid of the air here, and then there will be negative pressure here. So if this pressure is lower than the pressure of the rest of the building, the air of the building will end up entering the toilet. This is acceptable. What is not acceptable is that the restroom air goes out, and no, we don't want that. Okay, so that's why we need to have this exhaust that it has go all the way up. So there's having ducts going through windows, it's not an option. You will see this sometimes, but it's not legal first, and then it's disgusting. Okay, because if we are getting rid of our exhaust air through the window, then the neighbor upstairs will end up receiving all that air that we are getting rid of. Okay, so don't do that. So make sure that this exhaust pipe goes all the way up beyond the roof level. Okay, so I wanted to show you this, and then I wanted to show you how to deal with that. In the first assignment, we had like a supply duct in this side of the building, a return duct in this side of the building, and we didn't have any conflicts. But when we have constraints, usually those elements, those ducts, are along the corridor. And well, if we have this, so we have to make sure that there is no intersection between the supply and the return. Okay, so this is the lesson.